Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
It's a pleasure having Asaf Nachmias here, and he will tell us about the diameter and mixing time of critical random graphs.
Thanks. Thanks for pronouncing my name correctly. It's not that simple. So this is a joint work with Yuval Peres, and I'm very glad for the opportunity to talk about this here because this is work almost entirely done here, so it's fitting. So our starting point will be the Erdos-Renyi random graph, which you obtain by taking endpoints and drawing each possible edge between them, retaining it with probability p and deleting it with probability 1 minus p. And so this is a random graph, and we call C1 written there. We denote by that the largest component of this graph. And the classical result in the 60s, perhaps one of the first rigorous proofs of a phase transition, says that if you consider this model with P, which is C over N, then if C is smaller than 1, all of the components are at most of logarithmic size with high probability. While if C is bigger than 1, then you suddenly have a unique giant component of linear size, and all the rest of the components are of logarithmic size.
I'm sorry, that passes because this was done by Bolabash at C equals 1.
No, he did it with a log correction.
Right, but
For the
you
size
should
of the
say
window.
that.
No, for the size of
And
the
then Woodchuck did it very shortly after.
So what they-
Without the log.
did something.
What did
I
he
had
do?
nothing
So
to do.
so the
You should, I mean, the standard reference
that's
is
true.
Bolabash
Bolabash
and then
started.
Woodchuck.
I agree. Bolabash
So
started
I
this.
that is sort of, he had nothing to do with it. Aldous did something beautiful, but not this.
No, Aldous did actually precisely this. So
No,
what
but-
Aldous?
Well,
This
but
was already
you wouldn't
known.
This was-
credit it, I did
No,
it
no,
too.
no.
But
That's
Right.
I
no,
did
no,
it
no.
last
So
year.
I want to make it clear. Bolabash started the study of what happens inside the critical window. I should have written him here. But what he did essentially is looking a little bit above the critical window and showing that it is close. Woodchuck, Peedle, and Veerman proved for the first time that if you take the size of the largest component divided by n to the 2/3, this converges to a non-trivial random variable. This was the first time
sure,
this.
but you're not saying that it converges to a non-trivial.
No, that's true. Okay.
So actually, what it was that in
84.
1984, first Bolabash did it with a log, and then in 1985, Woodchuck did it without a log, not showing that it converged to a non-trivial random variable, but showing that.
I agree. I
So
accept.
that would be
Yeah.
those would be the standard references.
Yeah, true. I apologize to both of the people missing here. Yeah, that's true. So this is
Bill has
this.
trained us so well to
No,
say that
but-
he's not properly cited, that we just jump up and cite him if
Yeah.
he's not properly.
No,
cited.
but
Okay.
to sign in
Uh-huh.
97 for something which is done in 84.
Okay.
Okay. Let me continue. So the second quantity you can wonder about the sizes about these components is their diameters. So when C is smaller than 1, so all the components are of logarithmic size, and the largest one will have diameter which is square root of log n. Since there are a lot of them, there will be one with diameter of order log n. This is what Woodchuck showed in 1998. While the diameter of the giant component, in the case C bigger than 1, is of logarithmic order. So, and yet there's no reference, or we haven't found any reference to show what is the diameter of the critical random graph. Look at Gn1 over n. You have components of size about n to the 2/3. What is the diameter of them? So, excuse me, in number 2?
Yes.
Yes, the diameter, yes. So this is something a little bit harder to prove, which was proved recently, it's a good question, because you can say that there are components of logarithmic size which have diameter larger than the diameter of the largest component. Yeah, you do have components of logarithmic size, but you need to know what the constants in front of the logarithms to understand that indeed the largest component is the one that attains the maximal diameter. It's not a trivial result at all, and quite recent. So there's still
one constant is 2, the other is 1.
Yeah, there's a difference.
So statement 2 is your statement?
No.
Statement? No. This is not my theorem. This was all known before. So now that we know this background, the point of this talk is, or a message that I want to pass from this talk is that a lot of things in percolation on finite graphs and perhaps in previous times and specifically on the Erdos-Renyi random graph was somehow done mostly in combinatorial methods, and these methods a lot of times don't work very well when you're looking at c equals 1 when the graph is critical, and it was considered a long time as a difficult case. But I will show you, like, my message for this talk is to show you that a lot of things are in fact a lot easier than the supercritical case. And we will see very, very shortly that the size of the diameter of the critical random graph is n to the 1/3. And this will be an easy proof. Another quantity that you can consider when looking at components of the random graph is the mixing time of the component. So the mixing time of the random walk on a component is roughly the time it takes for the random walk. So we know that the random walk converges to the stationary distribution, and the mixing time is the time it takes it to get close up to total variation distance of 1/4 from the stationary distribution, where we consider the worst starting point. So recently, there's some attention been given to the question of what is the mixing time of the random walk on the giant component of the random graph. So independently, Fontoullakis and Reed and Benjamini, Kozma and Wormald proved that if you take this giant component, run a random walk on it, then after log square steps, it will be mixed. It will be close to the stationary distribution in total variation.
So this is this year. I'm just
So this is yes. This is so Fontoullakis and Reed so they announced this, I think, already in 2003 or 4, but the preprint is actually still not available. So there's half of it available. Okay, and the methods are completely different of these two proofs. Benjamini, Kozma, and Wormald found a geometric explanation for this reason, and the geometric explanation is that you have a linear size component, and how it looks is that what it essentially is, it is an expander on most of the vertices, and it has some tails, some little bushes of size logarithmic. If you know this, then it's not hard to guess this log square, because if you begin from one of these tails of order logarithmic, it takes you about log square time to get out of it, reach to the expander, and mix. So this is it, and they asked a natural question: what happens on the critical random graph? And so this is what the two holes that we've managed to say something about in this work, and this is the following theorem that tells you roughly what is the diameter and the mixing time of this critical component, the largest component of Gn1 over n. So the diameter is about n to the 1/3. It cannot exceed or be a lot less than n to the 1/3. And the mixing time is linear. This also extends if you look at the critical window. So if you consider not exactly p equals 1 over n, but if you consider some additions of size, if you add some 1 plus o of n to the -3rd. So the diameter, in fact, is not a surprising result. This was something that if you think about it, or people knew it. It is folklore, and the reason is because the critical random graph, the largest component, has some fixed probability of being a tree of size n to the 2/3, and it is a classical result of Renyi that a random tree on k vertices has diameter of order square root of k. So if you know that the critical random graph, the largest component of it, is not necessarily a tree. It could be with a few more edges, but it would be very surprising if these few edges would change. If these few edges would change. Okay, so this is the main result. Now we're yes.
Are you going to give us the explanation of why
Yes.
the mixing time should be order n?
Yes.
Similar kind of
I will,
heuristic
yes, I will give you a heuristic and quite almost precise
So do we
heuristic.
believe that it's really that big, or could it be n to the 2/3?
What exactly? The diameter?
The mixing time.
So-
Here, he's got
The
it.
theorem is that it's n.
No, it's
N.
Oh,
N.
it's not in the sense.
Right.
Yes. So,
Right.
mhm.
It's n.
It's at
It's
least n. The mix.
It's
No,
at least-
it's at least, it's at most. There. It's at least,
I
it's
see.
at
Mhm.
most. So it's order n, and
It's order n?
I mean, the n to the 1/3, even though I didn't know how to prove it, I thought that was known. But
I
you're
thought
right,
so-
for
I
the-
thought so
for
as well.
The heuristic explanation, no, I'm not saying I had any idea how to prove it, but the mixing time on the critical random graph, I'm just trying to think of the heuristic. I never thought
So
of
I will
that.
I will
That's-
explain, and
that's an
you
interesting
first need to understand that it's closely related to why the diameter is into the 1/3.
I'm
So
sure it is.
so well,
That's what I'm trying to
it's
figure
not a
out.
coincidence. Okay, but now we will.
Okay, good.
Is there? Yes.
So if you have a tree, a random tree on n to the 1/3 vertices, then how long is the mix?
N to the 2/3. So it will be if it's a random tree on k vertices, we'll have mixing time of order k to the 3/2. Okay, but we will discuss this. But first I want to discuss. So we will leave the realm of GNP, of percolation on the complete graph, and let's consider now percolation on a general d-regular graph. So they always ask me in Berkeley, what does d-regular mean? So all the degrees are d. Okay, so you have a d-regular graph, finite, on n vertices, right? And we write GP for the p-bond percolation on this graph. Here's the theorem. If p is smaller than 1 over d minus 1, and you do percolation on a d-regular graph, immediately you get these bounds. There will be no component of size bigger than n to the 2/3. Okay, this EFC is the number of edges, so the volume will not be bigger than n to the 2/3, and all the largest components of order, if there exists components of size n to the 2/3, which is not always the case, then the diameter is about n to the 1/3. And similarly for the mixing time. So what this theorem means, this theorem applies or says something not trivial only in the case where you have a d-regular graph and you percolate at 1 over d minus 1, and indeed you get some critical components of order n to the 2/3. This shows you that the diameter is of order n to the 1/3 and the mixing time is of order n. It's not necessarily the case that 1 over d minus 1 guarantees such components. For instance, the d-dimensional torus. And we will discuss this. Okay? We will see also, we will discuss how it extends. So the minute you know this theorem, for a general d-regular graph, you deduce immediately the theorem for the Erdos-Renyi random graph, because we know that in 1 over the degree, which is about 1 over n, components of size n to the 2/3 exist. And this was proven first by Erdos and Renyi. Yeah, no doubt about that. This theorem as it's stated here. But yes, yes.
So I'm just confused about which constants depend on each other, because for the complete graph,
So just
d is n doesn't matter.
so all of these constants do not depend on d.
D does not need to be bounded.
D does not need to be bounded. This is true for d equals n.
For every epsilon.
This is
A
this is
just
a
is the
yeah.
universal function of epsilon. Right.
Yes. It's just a function of epsilon. Nothing else involved. Okay. But the minute we know this theorem, we also know it for a few other cases. So not only the Erdos-Renyi graph, but almost any graph that you will choose on n vertices of degree d will have this property that percolation at 1 over d minus 1 will yield a component of size n to the 2/3, which has the correct diameter and mixing time.
But this don't know if d is bounded.
If d is, excuse me, so this is only known if d is bounded. Correct? And also another example, which was given recently, is if you take two complete graphs instead of one, so the Erdos-Renyi is 1, take two complete graphs, consider their Cartesian product, and this is a model introduced by van der Hofstad and Muchak, but effectively, essentially, the fact that at 1 over d minus 1, that there exist components of size n to the 2/3 was proved in Borges, Chase, van der Hofstad, Slade, and Spencer in a far more general context.
What is the Cartesian product?
So think of it's like ZD, only instead of Z, take the complete graph. Well, best explanation by example.
And there is some randomness, or you do a percolation?
Of course. So this is a fixed graph, and here it's also you.
Just like before, it was a complete graph and you percolated on it to get GMP.
So
Here it's taking the
Are
Cartesian
you
product.
if I'm an edge in the product, if I'm an edge
So XY
in
is
either of them or in both of
in
them?
one of them.
In exactly one.
In exactly one
The
of
other
them.
one I'm equal.
Otherwise, you're the same. Okay. So now that we have this, I will try and convince you will be a proof that the diameter is of order n to the 1/3. We will see how this follows essentially from a very classical theorem about branching processes, and this is, I think it's the first theorem I learned about a branching process when I was younger. So. So you take an infinite d-regular tree and consider critical percolation on it. So an infinite the root has degree d, and all vertices have degree d. But okay, so take an infinite d-regular tree, consider percolation with So this is something that I forgot to write here. P equals 1 over d minus 1. So and consider the levels. The survivors in this branching process. Okay, so LK is simply you look at the kth level of the tree, and this is the vertices who are attached by a path that survived in the percolation to the root. The theorem of Kolmogorov says that if you have forgive me, what is required here is P equals 1 over d minus 1. If it's a critical branching process, the probability that it survives up to level k is roughly 1 over k, some constant. Okay, how does this yield a bound on the diameter? Let's just write a few definitions, and I will prove this on the board. So if we have the definitions are the following: if you have a vertex v in your graph, so now we're in the context we have a d-regular graph. P is 1 over d minus 1. C of v is the component containing v, and we write this metric dpu of v. I don't like using the laser pointer. And we just defined the ball around the vertex v of radius k. Thank you. Of radius k in the internal metric of after the percolation. Okay, not in the metric of the original graph. And similarly, we define the boundary.
So these are random geometric.
These are random geometrical objects, but we can very easily bound these things from above by our branching process. Okay, so because the graph is d-regular, so we think about how you explore these levels. At the first step, you have d neighbors, and you can always use these random choices to do percolation on the infinite tree. Okay, so in this way, the amount of vertices that you have up to level k in the infinite tree is obviously an upper bound for the number of vertices you have up to level k in your d-regular graph G. Okay, so this is all what we need to know. Oh no. Yeah, I've learned this. So now let me show you that the diameter is of order n to the 1/3. I hope this is still visible, more or less. So we fix a vertex v, and let's begin with considering the component that contains v, not necessarily the largest component. So the probability that the diameter of this component is bigger than some number r. So what it means is that the boundary of distance r over 2 must be non-empty, right? Because there has to be, of distance r over 2, you have to have a vertex. So this means that r over 2 is bigger than 0. But now, this is Kolmogorov's theorem, right? Because of this bound, and Kolmogorov's theorem, we immediately get that this quantity is smaller than some constant over r. Okay, this is nice, but it still doesn't tell you anything about the largest component. But here's a trick. You consider x, let's consider it as, let's say it's the number of vertices such that the size of their component is bigger than m, and also their diameter is bigger than this r. This is the number of such vertices. So we immediately deduced by this calculation that the expected value of x is smaller than nc over r. Very good. Yes? Questions?
N is.
Did you
N is the number of vertices in the graph.
This is independent of m.
This is independent. There is no m still. I just wrote it as a parameter. But now, okay, the probability that the largest component, the probability that you have a component, exists a component of size bigger than m and diameter bigger than r, diameter bigger than r, this event implies that x is bigger than m. Because if you have one component that the diameter of this component bigger than m, such that the diameter of it is bigger than r, then you have at least m components, because every vertex there counts for one. M vertices, sorry, that contains this, that has this vertex. So this is the probability that this is exactly what we need to prove. Okay, so this is smaller, bigger, smaller, than the probability that x is bigger than m, which is hence smaller than NCRM by Markov's inequality. Correct? Now, put r, which is a n to the 1/3, and m, which is some fixed constant beta n to the 2/3, and what we get here immediately, the n's cancel, and we get some c over a. Take a large enough, and this proved to you that the diameter is no more than n to the 1/3. Sorry? Yeah. So I will use 1c for all constants. It's going to be a lot. Okay. So this is a simple proof. But let's see how this, something which is a bit counterintuitive, that how this upper bound using a branching process yields a lower bound on the diameter. Okay. So it will be a trick of a similar nature. And let's do that. So again, our starting point will be considering the component that contains a certain vertex. So what we're going to consider is what is the probability. So you have some fixed v. What is the probability that the diameter of c of v is smaller than some number r, little r, and that c of v is bigger than m. So what it means is that if you look at the levels from v, if you look at after little r levels, you have already m vertices. But look at this. Okay, the number of vertices that you encounter after, so this k will match the little r. has expected value, which is some constant times k, because this is the number of vertices that you will see after k steps in a critical branching process, and expect on average. So what it means is that this event implies that the size of the ball surrounding V with radius r is bigger than m. Okay, but we know that this random variable has expected value which is about constant times r. So this will be smaller than CR over m. Now we proceed in the similar fashion. Once we have this, let y be just the random variable counting the vertices that have this property with diameter C of V smaller than r and size bigger than m. Oh. Now I bet you can guess the rest. Yeah, that's all. So the probability that there exists a component with small diameter but large volume is going to imply that this random variable is large. So the probability that there exists a component bigger than m and with diameter smaller than little r is going to be bounded. So I forgot to say that. So what we've concluded. Bounded. So this will imply that y is bigger than m.
Yes.
Of course, I forgot to mention that the expected value of y is bounded below by n times this number above. Sorry, right? Yeah. N CR over m. So this let's put it. So this quantity will just be bounded above over m squared. Now again, take m equals beta n to the 2/3. R is going to be some small constant, a to the minus 1 times n to the 1/3. Again, the n's cancel each other, and what you're left here is just some constant, different constant over a.
Very nice. I have a question. When you sort of in the simple random graph want to prove that at criticality the largest component is the order n to the 2/3.
The size.
The size.
So this is my next.
One directional bound is sort of usually easy using bounding with branching processes, and the other direction is sort of difficult. So can you do a trick like that to actually?
Yes. In fact, once you have these two tricks that I've shown you, proving that the size is not larger than n to the 2/3 is almost immediate, because
Not larger is larger or equal. That's also immediate.
so larger than n to the 2/3.
The way that you don't get with the branching process.
Oh wait, so you're talking about the lower bound, proving that it is indeed bigger. So this is we did some other work which is not as simple as this, but indeed lower bounds are harder.
So this trick, well, here they work for upper and lower bounds. So what
It does
makes
not. It does
work
not.
so
It does
much
not.
easier
It does
than
not
the-
work.
So
It
why
just.
does it work here and not here? It's so pretty actually.
Yeah, I'm asking myself the same question many times and many different examples.
Yeah, it's
The
really.
answer is that here you're feeding the lower bound for the volume. So you
I
use
see.
the fact that you know that there is a component of size n to the 2/3.
Okay. Nevertheless, it's really
Yeah.
cool.
Yeah, that's true.
I see.
You
So
use
that lower
every
bound
time.
process upper bounds tells you a lot.
That's a good answer. Thank you. You use the fact that you have a component of size n to the 2/3 in all these calculations. Otherwise, it doesn't really matter. Okay, so this is the diameter, and let's see how. So, given that you know the diameter, so let's go back to this lighting. Given that you know what the diameter is, you can have an upper bound on the mixing time, and the upper bound follows by this fact. This is something. So we did not invent this. This was known before.
Did
Yeah.
you show us all the parts of the theorem? You had 3 parts. And maybe
Yes.
one
No. I showed you just number 2.
2 and 3.
2 and 3. Yes.
But not 1.
So I haven't shown to you So I told you that the diameter is bounded by n to the 1/3. And first let me state the theorem. The mixing time of a lazy, simple random walk on a graph is bounded essentially by the volume times the diameter. This bound is horrible in any other case but trees, or random trees. So this bound is usually immensely, very not tight, but it gives you the correct order in this case. So I haven't proven to you that the number of edges, this is the number of edges in the graph, is of order n to the 2/3. But this kind of trick will prove it, because either the component has either it has a large diameter, or it has a small diameter with too many vertices. Okay, if you know this trick, you can immediately get the number of edges. This is also something we did in a previous work to show a simple proof that the number of edges does not exceed n to the 2/3. So the minute we know all that, of course, you get an upper bound of linear size on the mixing time of the graph. And indeed, any questions? Okay. So now let's talk about the lower bound on the mixing time. So the lower bound is also, well, of order n, and I will sketch you a proof. So this is a little bit more complicated, and let me explain where the proof comes from. So you need to know something about the structure of this critical random graph. So what we do, we know that it is a graph on n to the 2/3 vertices that has diameter, which has diameter about n to the 1/3. Okay.
Could you say again?
So it's a graph on n to the 2/3 vertices of diameter n to the 1/3. So let's draw it, and what we're doing is the following. Okay, so this is our vertex v. Choose some vertex. This is of height about n to the 1/3, and we're going to choose a level, some level r. So all the levels are going to be some constant times n to the 2/3. And what we're going to require is that the number of edges here is going to be smaller than, say, a third the number of edges here. So most of the mass of the component is here, in this section. So this is most of mass.
With respect to edges?
With respect to edges. It doesn't really matter. Yeah, it's going to be the same order. But with respect to edges. But still, what we have is that the fact that but still here we have some constant times n to the 2/3 vertices. So now I claim that it suffices to bound this is it, the expected value of this random variable, which is tau, I call it tau r. And tau r, this is going to be the hitting time, starting from the hitting time of level r. Hitting time okay, so it suffices to show that this is bigger than some constant times n.
Could you explain again? So you have this picture, but it has repeated vertices in it, right? It's not a tree what you have, the component.
It's not a tree.
So the V, for example, may appear.
No, but
Not repeated vertices.
it's not. You just look at the levels. Okay, you look. This is r. Is all
how far away
all
it
the
is
vertices? All the vertices of distance r from v. There may be. Yeah, it's not a tree.
So you're not. Okay.
Not assumption. I'm not assuming that it is tree. But so now, if we know that the expected time beginning from this vertex to exit this level r is bigger than some constant times linear, I claim that this tells you that the mixing time is bounded below by some other constant times n. And the reason is because if the mixing time was smaller than some very small constant, then because most of the mass is here, you would have had, from any point in here, you would have had some reasonable probability, say 1/3, of exiting. So what you can do to bound this exit time starting from v is just do it by iteration. Take this small constant times n, ran a random walk. If you haven't exited, do it again, and do it again. So each time you have probability 1/3 to exit. So this random variable is bounded by above by t times a geometric random variable with mean 3.
Why do you even need to do that? Isn't the mixing time defined as the mixing time with the worst starting point?
So I'm actually using this definition because I'm saying that if the mixing time is smaller, then from any point here, I will have some good probability of exiting. So it's not.
He's proving to you that it is the case.
But if I start from V,
yes.
Mixing time doesn't involve expectation.
Yeah, mixing time is
The
actual
expectation should not be
distribution.
there.
Right. No.
No.
it should be.
The
there.
point is.
The point is
Oh,
that
it should be
the
there.
point.
The
This is,
mixing time definition does not
Yeah.
allow
So-
the
so
expectation.
if we,
Okay,
You're looking
thank
at
you.
The point is, the random variable could be small and expectation could be large in general, and for this kind of variable, that's impossible.
mhm. So again, the expectation is important. Well, we know how to handle expectation better than we know how to handle this PT. Okay, it's hard to say where exactly PT, where the distribution of where the particle is going to be after t steps, and what you compare in total variation to the stationary measure. So once we've realized that, so all we have to do is to estimate this expected stopping time, and here comes to our help a lemma of Titali, which gives you an equality given the effective resistance of this network. It tells you and it gives you an equality of the expected hitting time of any point in a network. So what we're going to do, so here it's z. Our z is going to be all this level. We can glue it together. This is what we need to prove. We're going to use this. Okay? So now let me zoom in a little bit. Draw it again, but this time this is R. So all of this is going to be level Z. And we want to bound from below the expected time starting from V of hitting Z. So this is the formula, and you can observe because the effective resistances on the network is a metric, all of these summands are positive just by the triangle inequality. So what we're going to do is the following. Observe that we're summing over vertices in the graph, something of this expression. And there's a general fact, which is not very hard to prove, that the effective resistance is bounded above by the distance between U and V. This is always the case. So what are we looking for? We're looking for some level even smaller that has about some constant n to the 2/3 vertices. And these are going to be our U's, so that what we can say about these U's, which are going to be very close to V, is that, so this will be small, this amount. Oh, thank you. But these will be big. So how do you bound from below effective resistance? So the canonical way, or just a way to bound from below the effective resistance is what's known as the Nash-Williams inequality. So if you have a vertex here, this is U. Mm-hmm. So what the Nash-Williams inequality says is the effective resistance between V and U, if you can find a lot of cut sets of small size, then it has large effective resistance. So all we need to find in this picture, so we have this vertex U, we're going to have a lot of them. All we need to find is we're going to find many levels here, and how many, it's going to be some other constant, bigger constant times n to the 1/3, such that if this is one level, such that there are going to be very few edges starting from here that actually traverse to the end. Okay, so once we have that, there are going to be many of these levels, about n to the 1/3.
What do you mean by an edge traversing?
So what do I mean is that if you're in a vertex here, so you can reach from this edge, you can walk without going back. You can walk on the graph up to level R.
And you don't ask that of different edges that is joined.
No. the minute I'll find about n to the 1/3 levels where each has some constant number of edges that can go to the end, this is a cut set, right? Because all the edges here that goes to the end, they separate u from z. Correct? So the only point is finding a lot of these levels such that only few vertices reach the end. But now we can use the same tricks as we used before with the branching process, because if we require here we have about n to the 1/3 levels, but if we require that here there is another n to the 1/3 distance, and all the constants need to be put together in such a way that it all works out, but this is just true, so it works out. So the probability of having a path from here to here is about 1 over n to the 1/3. And you will have about n to the 1/3 vertices here. So this is just Markov's inequality. And then a bunch of other Markov's inequalities to find more levels like this. And then you get about n to the 1/3 cut sets, each of constant size, which tells you that these quantities for these u.
That's what he said he had.
Didn't you need n to the 1/3 safety band up to the...
So I need n to the 1/3 strips, each having constant number of edges going above, going to z.
Oh, but you don't need... So n to the 1/3 is the volume of the strip or the diameter?
No. So the strip is just the strip is just between level k and level k plus 1. It's just.
Number of strips.
But the number of these is going to be, I'm going to have n to the 1/3 of these, each having constant number of edges that reach to the end. This gives you a lower bound on this. So of course, if you manage all the constants together, this is going to be small because we chose them close to v, and these are going to be bigger because we have proved that there will be many cut sets.
So the distance of u from v will be
Some-
n to the 1/3.
Will be small constant. So
Small constant.
small
times n to the
constant. It's important that the constant times n to the 1/3 will beat this constant. Okay, it's all inequality. This one.
And you said that show that there are many levels k plus 1 that have this property.
Uh-huh.
You said that you use some other Markov's inequality.
Yes.
You mean that you use some variance bound? You want
No,
a lower
it's
bound.
just it follows just as simply. Just because of what you know that the probability from it's a little subtle. I agree, and we have worked a lot on understanding these subtleties, making many mistakes in the road. But it's just from the fact that you will, on average, because this tree is large, so you will on average have here n to the 1/3 vertices, and from each vertex here, the probability of getting to here is n to the -3rd. So the expected number of these edges that go all the way is constant, and this will be true for every. So it will be. It's a similar argument to the lower bound. You want to show that they exist. That's why I understand your question about the second moment. But it will be very similar to what we did with the lower bound on the diameter. The upper bound will give us an existence. result.
You said in this tree, but this is not a tree.
Sorry, this is not a tree.
It's not
But
a tree.
it's not a tree. It's just an edge that goes from here, reaches to the top without going below level k. This is a cut set.
So are we in a situation where we're conditioning V to be in
No.
large
I'm just using the word conditioning as intuition, but it's not really the case. The proof itself is a little bit more. This is a sketch.
Oh, it's a sketch.
It's a sketch. It's not a complete proof. This is what happens, and it's a little bit to prove it exactly. It's a little bit messy, but these are the ideas.
Okay,
Mhm.
now I understand John's question. So the fact that you have one strip of
Yes.
n to the 1/3.
Mhm.
I mean, on one cut set you have few edges.
Uh-huh.
Okay, that's fine. But how do you, when you show that,
So
you kind of
Yeah,
think that
I-
these are independent?
I don't.
So you have many.
I don't want to show this. This is the main body of the
Right. I was
the main
more
the main
that you
work.
needed to go this n to the 1/3.
No.
before you get the next
No. They will be close, and
So they're not independent.
they're
You
not.
don't
It's not
need-
independent events.
They're
No, they're not. But they do exist. It's an argument similar to the other argument. I just don't want to go into it because it'll take me a while to finish.
Yeah, they're not going to be independent because they're going to be using the same.
Yeah,
I think
of
this
course.
is sort of the magic of power laws. If you count something and then you count the number of vertices in it, it gets multiplied by a power, but it all works nicely out.
Yes.
Anyway, but the levels
Uh-huh.
you find are
Sorry?
like separated from each other by up to 1/3.
No. They're close.
Okay.
They're
Typical level is good.
a typical. Yeah.
These are not exceptional levels.
These are not.
Yeah.
Most levels will be like that.
Yeah,
Mhm.
and they're going to be using the same
You
path.
don't need a second.
Yes, the same paths.
Okay, so
They're-
the
they're-
extra 1/3 that you
Yes,
find
of course.
is just
I mean, once you
why
find a
is the
few of them,
1/3
of course,
not
you
more?
Mhm.
Because the whole diameter
Yeah,
is
yeah. That,
I mean,
the-
you just cut above that
yeah,
path.
yeah,
and
yeah.
you're
Of course.
gonna
Every,
find more.
yeah,
the
they're
volume.
positively
Right,
Right,
correlated.
because
You could
once I
say.
know there are all these paths, all I have to do is keep cutting, and
Yeah.
there are going to be more paths like that,
Absolutely.
right?
Mhm.
So they're absolutely not independent.
So this shows the mixing time is bounded below by n.
But look, they're using, once you know there are all these paths, cut again, when you're going to be cutting those paths again, you're going to generate
let's-
something like that again.
Let me show you something interesting before I finish. This will. So what we said is that you have a deregular graph, and if p is smaller than 1 over d minus 1, then you can, and you have components of size n to the 2/3, then they have diameter n to the 1/3, mixing time of order n. But in fact, you don't really need the condition. What we use here is essentially just these critical exponents. All we use in this proof is the fact that in the internal metric of after the percolation, the probability of having something at level k from you decays like in a tree at some constant over k. Where is this when I need it? And the fact that if you look at the ball of radius k, it behaves, the expected value of it behaves like a linear in k.
So,
These are
but
all the facts.
These are like all high-dimensional lattices. that are
Exactly. So this leads me to my next
It's
question.
not known
Okay.
that high dimensional.
Then if you have all you need to know, you don't need to know that p is 1 over
But
d
I mean,
minus
presumably,
1.
I don't think other things do satisfy.
The graph does.
Hypercube should satisfy.
But the hypercube is high-dimensional.
Yes. Yes.
I mean,
So
So
let
in
me.
2 dimensions, this would be false.
2 dimensions. This will be false. Absolutely.
yeah.
But if you believe the hypotheses that in high-dimensional tori you have this tree-like behavior, the critical exponents assume their values on a tree, then you can ask what indeed happens on the tori. So this is a result of Borix, Chase, van der Hofstede, Slade, and Spencer from 2005, which says take the d-dimensional torus with side n. Okay, we wire it so it will be transitive, and so they proved that if there is some value pc such that you have a similar phenomenon like in the Erdos-Renyi random graph, i.e., you can move inside this window of order volume to the minus third, and still get that component size is of order volume and volume to the 2/3. And the questions that we're asking, which would be wonderful, does this PC have properties, these properties? The minute you will know that, immediately you have this. And moreover, you can deduce, because of this structural thing, you can deduce what is known in the physics literature as the Alexander-Orbach conjecture, which says that so roughly it talks about the incipient infinite cluster, but you can translate it into critical clusters of the finite torus and say that, and what it says that if you have a random walk on this percolation cluster and you run it t times, the number of vertices that it visits is about t to the 2/3. And this all comes out from this structure, and it's equivalent to several things that we've seen. So this question will be, well, if we can verify these, we will have that result. And I think I'll finish here now.
Some of those, I mean, we have shown that the largest cluster has size v to the 2/3.
Yes,
right?
that's true. This is.
So didn't you in your first argument essentially only use,
p smaller than 1 over d minus 1.
So we don't know that the effective branching process here is subcritical.
No. The branching process is not relevant.
But
It's
on
not-
these substitutes, it probably.
But if you just know this.
Yeah, but those are, I mean, I agree with you, that's why I said that's high dimension, that's kind of,
Right, but
that's,
it's
it's, oh, I understand, I mean, I know how hard it was to prove the other stuff, but I'm just saying, when you look at those to me scream high dimensional behavior,
So now it's sort of interesting that one would think that the lace expansion gives you enough control.
Yeah, I think that there should be enough control in the lace expansion.
Well, I mean, I just know from experience that we thought several times that the lace expansion should give enough control, and was a lot of work to write this up. And
Right. So I think.
Yes, and yes, we want.
This is why they wanted us to see the top.
But right. So the problem is that with the lace expansion and triangle condition, what hasn't been done so much is working in the intrinsic metric of the cluster, right? So results were written in terms of the extrinsic original Euclidean metrics. But one thing we would believe is that high dimensionality mean field triangle condition, these kind of conditions should imply this 1 and 2, which are facts about the intrinsic metric.
Yeah. We'll try to get some differential inequalities that would imply this, but we don't know how to do this.
But it would have to be like finite size differential inequalities, which are much harder than just this.
is that infinite volume analog of this?
Yes. So these things you can ask for ZD at PC, and if you know that.
And what are the differential inequalities?
So there is no. I don't know of any differential inequalities that give you. Even in, especially in, even in the infinite volume, that would.
Because those just usually have zeros.
Yes, I mean that would be a good. It's interesting in both scenarios, both the finite and infinite.
So, but if you had these inequalities in the infinite volume, could you deduce these things about the?
No.
I think it would be more work.
No, you could deduce about finite clusters in the infinite volume. So you look at the critical cluster.
Yeah, but
it's
still
finite.
wouldn't be enough. I mean, this is.
You could.
No, it would be enough for the finite, not for clusters on the torus, but you do critical percolation in ZD. Look at the finite cluster of the origin. If it's big, what is the mixing time there?
What is the diameter? What is the diameter of critical? This is something even in 2 dimension. I don't know the answer.
And then there's all this Eisenman stuff about what you mean.
So yeah, this is all.
So just to understand myself, although everyone else already does, so you conjectured that in D 100, then ZD satisfies these.
Well, if you want me to conjecture, I will conjecture D bigger than 6, but.
You can supply the missing
We
bound, but
showed,
100 is bigger than
what
6.
our theorem showed was that for D large enough, and you could take it down.
No, but not this.
Not this, no, for our stuff, and then you could take it down in various ways by making it not just nearest neighbor,
But you conjecture it's
nearest
provable
neighbor
using
thing.
the lace expansion?
I
What?
conjecture that for large enough D, it will be provable by later. I hope so.
I think
I mean,
it might give that.
this is.
So he just conjectured that just with the lace expansion and not the axiom of choice, you can prove that
Throw in the axiom of choice as well. No problem.
Gabor is gone, we can throw out the axiom.